Hello, and today we are going to do Thevenin's theorem, which is one of the last circuit analysis that we can do. Okay, another thing that I didn't mention in the previous videos is that Thevenin theorem and superposition and mesh as well, I think it is, can be only applied to linear circuits, which basically are circuits that have DC power, where the power is just a straight line. You cannot apply them where the power is an AC, because it will be, a sine wave. You can still apply node analysis and the other ones to it, but you can apply Thevenin superposition or mesh. But we'll talk more about that when I get to AC, I guess. Anyway, so now let's do Thevenin theorem. Thevenin theorem is like one of my favorites to do because it's simple. It's like superposition, but it's more useful because it simplifies a circuit. It makes any circuit into a series circuit, and you can easily find out the values like of current going through RL or the voltage at RL and stuff like that. Anyway, so I'll show you this with like a simple example, which is this one here, and really it's only one step, and that's like choosing the resistor. You can choose any resistor really, but we'll start with the simple one. So we'll start with this resistor, with this unknown resistor RL. So let's do here two nodes. So this will be A and this will be B. All right, we got the two nodes. And now the first step you do in this is to separate the voltage and the resistors. So our next step is to, like in superposition, make the voltage sources or the current sources in a short. Then we'll get something similar to this. This is the resistor, this is the other one, and here is the opening. There and there. This is 12 ohms and this one is 6 ohms. Okay, and yeah, as you can see, now we can calculate the total resistance. But this resistance, we'll call it RTH. And that one will be equal with R1 in parallel with R2. And that will be equal with 6 in parallel with 12, which is equal to 4 ohms. So RTH is equal with 4 ohms. So you're gonna need to remember this value here for later. And now we need to calculate VTH, which is called we still do apply this something similar to this. So let's do the diagram, because why not? So here it's like 18 volts, goes up here, it goes through a 6 ohms, and then it goes down to the 12 ohms, and here are the openings. And here's the interesting part. Basically, there is no current going through this opening because it's not really part of the circuit. Therefore, we can see this circuit as a series circuit, that the current will go in this direction, then it will go down. It will not go through there, which will make it a series circuit. We can put the ground here as well if you want to. So it will be, R total will be equal with 6 plus 12, and that will be equal with 18, and then we do 18 over 18, and that will give us 1 amp. And now we can easily, now how do we find the value of VTH? Well, the value of VTH, it's in here, it's between, so VTH will be this value here. And as we know in the laws of like circuits, is that resistors that are opposite have the same voltage. So what we need to do is to find the voltage inside the 12 ohms, and that will be pretty easy because it's a series circuit. So we can simply do 12 ohms times 1 amp, and that will be equal with VTH, and therefore VTH it's equal with 12 volts. So now we have both value. We have VTH and we also have RTH. Now we can reconstruct the circuit with the new values. So VTH will be equal with 12 volts. There goes back to focus, okay. And then we put the RTH, which is equal to 4 ohms. And then we put RL. And that's it, that's our circuit. And you may wonder, like, well, what's the purpose of this circuit? Well, depends. When you build a circuit, and let's say this is from where the circuit, like, you want this resistor to have a specific current through it, or you want to have a specific voltage in case it's like connected to something else in parallel. Well, a good example of that will be inside op amplifiers, because you got two op amplifiers, and one of the op amps is actually made out of only resistors and a DC voltage. So we can like use this Thevenin theorem and manipulate to make sure we got the right voltage that we want in both sides of the op amp. And the idea is like Thevenin theorem is good at discovering the values of one resistor and building around it. For example, if let's say we made RL 10 ohms, yeah, then it will be an RT, our total, of 14 ohms, and then the current will be equal with 12 over 14, and that will be equal with, just a second, 12 over 14, 0.86 amps. So now we know that through this side here, 0.86 amps are going through, which means that the voltage inside here is 8.6 volts. So we already know two important things about this resistor here. We know that the current going through it is 0.86, and that the voltage through it it's 8.6 volts. If it's got the value of 10 ohms, and you can replace it with any value in here, and you can easily determine the new current and new voltage. Let's say if you apply superposition to it, like if you solve this problem knowing this is 10 ohms and you apply superposition, well, that make it very complicated, because what if you want to change it to 20 ohms or like 30 ohms? Then you need to recalculate everything again to know the value, to know the voltage and current going through this resistor. While with Thevenin, you can easily recalculate it by just dividing the voltage by the resistance to get the current, and then just multiply the current with the resistor to get the voltage inside of it. And these are the basics. So if we can do like a recap of it, we can write down the steps. So let's say step number 1 will be to choose the resistor. So choose the resistor. It can be known or unknown. It can be both. You can know it or you can not know it and determine it later. And then step 2 will be find RTH, and then replace V source with short, and replace current, let's just put IA source, with open, just like we learned in superposition. Then that's the second step. The third step is like to determine VTH, and remember that RL is a open circuit. Open circuit, so there's no current going through it. And then step 4 is to like put it together, put it to there, like in this one here. So I'll see these are the simple 4 steps. First step, choose the resistor and put the 2 dots here, A and B. Then step 2 is to calculate RTH by replacing the sources. Then step, okay, and you may wonder like why it's here parallel. Actually, yeah, I should have explained that as well. Like why it's parallel in the first one, in this one, when calculating RTH, but it's in series in this one. Well, it's a bit complicated and I don't know how to explain this well, to be honest. Because when you calculate RTH, it's like pretending there is still a resistance in here, but it's just that you can't see it and it doesn't affect the circuit because it's an unknown resistance, you know, but it's still here, which will make this one a junction, which will mean these two are in parallel. However, when you are doing it here, then that resistance doesn't exist. Like it's seen as there is no resistance, that's why there is no current going through it. I know it sounds weird and it's complicated, so yeah, so let's write it here. So let's put like an X arrow like 5. Okay, when finding RTH, okay, let's see, RL is short circuit, and then rule number 6, when finding VTH, then RL is open circuit. Okay, and okay, so we add the other 2 rules to it. I mean, it does have more rules than the other ones, but as I said, it's more useful than the other circuit analysis methods. And you can like work yourself backwards if you really want to know all the values for all of them. But usually in a circuit, you don't always need to know all the values inside the circuit. You don't, unlike, let's say, you don't really need to know the voltage inside R1 or the current inside R1 and R2 specifically. Sometimes you just need to know the current inside a specific resistor like this one here. But yeah, so this is the first start. This is the the groundwork for it, let's say. That's why it's a simple one and easy to determine. And so on the next ones, I'll pump them up in a difficulty, and you'll see, you'll better understand it. That's why I'll do 5 examples of Thevenin theorem, because I see them as extremely important, and it's also good practice for like superposition, since they use basically the same method, you know. And anyway, I'll pause here and I'll go to the next page. Okay, so here's example number 2, and as all examples will be different. So on this one, I'll show it to you that you can calculate using Thevenin theorem the resistance, any resistance inside the circuit. That's why we're going to choose, strangely enough, a resistance in the middle of the circuit. I watched a few YouTube videos about it before, and I noticed that nobody ever does that. Like, I haven't seen a video that chooses a resistor in the middle of it, and this kind of like circuit will open a lot of like new ways to look at it, because it's very different. When you choose a resistor like this one here at the edge of it, then it's really easy to visualize it and do it. But when you choose a resistance that it's an unconventional place, like it's not to the extreme right or to the extreme left, then it's a bit more complicated to do so. But don't worry, this process, it's also simple when you know what to do. So we did first step number 1, which is choosing the resistor. Now let's go to step number 2 and calculate the RTH. So we can transform this circuit into this one, which will be like that. This will be, we'll mark the 2 points A and B. Then there's another resistor here, this one will be a short. There will be another resistance here, which this one will be very interesting. I'll show in a second. So that will be 4 ohms, R3, then 8 ohms, R2, and then 12 ohms, R1. Okay, this is ohms. Yeah. Anyway, so why is this interesting? Well, because it's a short circuit in here. Even though we have only resistors, we can still get short circuits in a system. Why? Well, because when you do 4 in parallel with 0, it will give you 0. So even resistors with no current or voltage can still give you short circuits, giving you answers that are similar to 0. So by knowing this is a short circuit and knowing this section is invalid, we can again redraw it. And let's make it even simpler. Instead of having one resistor this side being the Thevenin resistance, let me actually write it here. So RTH, this one being RTH, and then this one being the 8 ohms going like that, all two of them in parallel. We can also write it like this. We can write RTH, and then one resistor here, and one resistor here. And that will make it easier to visualize and understand, because even though they are in parallel in different sections, even though they have RTH in the middle of them, all three of them are still parallel to each other. So we can rewrite it like this and make it a lot simpler, because now we can just do like 12 parallel with 8, and that will be equal with, wait a second, because I have the answers here. There you go, 4.8 ohms. Therefore RTH is equal with 4.8 ohms, and this is one of the values that we need to remember. So let's like square it up. Yeah, now I also like checked, like they're still randomly, like I still put random values inside the resistors and the voltage sources and everywhere, and I still like draw it randomly. But now I calculated beforehand, so the videos will be a bit shorter than before, especially since there are like 5 examples in this one. I did 5 examples for this one, so yeah, it will go faster through. You also want to see me like keep calculating. I'll calculate when I have like, when I want to do something that I'm not prepared for. Anyway, and also this the answers are also to check myself, so I don't need to come back and see if everything is right, or if I get the wrong answer, I don't need to like pause the video, look through my notes again, and then like keep going. Anyway, now we know RTH. Now we need to find out the VTH, so we can again write it like that. So we can write it in this form. We can write it like this, so that would be a, let me just note the muscle, AVTH, and then this point will be B. Okay, then there will be the 8 ohms, there will be like the 12 ohms, 8, 12, then there will be the voltage source, which is 16, which is a minus and a plus here, going down, going that way, and then the 4 ohms. Let's write them like R1, R2, and R3, and here is the ground. Okay, now if you look at it, it's kind of hopefully you can see what we need to do. We will basically need to find out the value of voltage inside R1, because R1 is perfectly in parallel with VTH, and because they are in parallel, they have the same voltage. Okay, so we can redraw this one again to make it simpler for you, as like this. So there is 1, there is 2, then there is the source 16 minus plus, and then there is another resistance. Okay, and there is the ground here, and this one will be 4 ohms, this one will be 8 ohms, and this one will be 12 ohms, and this one will be minus plus VTH. Okay, So volts. So now we can see how we can calculate this, and there are multiple ways to do it, but I'll show you like the simplest way, which is adding those two together to give us 20 ohms. So there'll be 20 ohms together, and then we have the 4 ohms in the parallel. So we can find RT, we can do 20 parallel fall, and that will give us 3.33. Okay, and now we need to calculate the current, and that will be 16 over 3.33, and that one will be equal with 4.8 amps. It seems about right. Okay, now we need to calculate the split in current between them, and we can apply the same method as I showed you in previous videos. I usually like to do this quick drawing. It makes it simpler. So this 20 in one side and there is a 4 in the other, and then 4.8 is coming in, so it's 4.8 times 20 over 24, so which is the total of these two, and which is equal with 0.8. Oh no, wait, actually no, it's not 20, it's 4. There you go, this one is 1, which is equal with 0.8. so 0.8 amps are going in this direction down here, so that means that 4 amps are going in this direction. We don't really care about this one, we care about this one here. So this will make it simpler. So then VTH will be equal with 12 times 0.8. So VTH is equal with 9.6 volts. Let's box it again. And it's our VTH. So we found our RTH and we found our VTH. Now our final step is to redraw it. So this one is up here, so it's 9.6 volts. Then it's RTH, which is 4.8. RTH, it says VTH. And then here it's RL. There you go. And again, and now we found out the value of RL, which is this one here. So now whatever value we give RL, again like 10 ohms or 100 ohms or any value, we can easily determine the current and voltage going in this direction. And because we can determine the voltage is in this direction, in this resistor, then we can easily determine the voltage inside this one as well. And because we know the voltage inside this resistor, then we can determine the current going through both. And because we know the current, then we can determine the current and voltage inside this one and this one as well. So basically all of it is connected, like they interconnect with each other. So yeah, but again, this is still a simple circuit. Like you can still do this easily with superposition or with node analysis. However, like in example number 3, I'll go to a more complex circuit that it really shows how Thevenin theorem can be useful. And so let's do a quick recap. So we chose the 2 points on RL. Then we redraw the diagram with RTH to find the resistance. We determined that this is a short circuit, so this resistance doesn't apply, and that all 3 of them are in parallel with each other. We found the parallel value between 12 and 8. That will give us the RTH. Simple enough. And then we did try to find out VTH by switching places with R1 with RL. And then we easily determine the current inside of it, and therefore we easily determine the voltage inside this resistor R1. Okay, this was example 2. Now I'll go to the next example, and I did this one to prove to you that you can choose literally any resistor, and to also show you, like, if you choose a random resistor, how to apply it and how to calculate using it. All right. I think the only condition is it has to be in parallel with something. I'm not sure if you can actually use R2. I should look into that. But I don't think you could, because it will break this circuit here. And then as a result, there will be only these two. I mean, it might still work. As I said, I'm not entirely sure. But I think it will work, and I think it will give you like a voltage of about 16, doesn't it? Or give you a voltage of 4. Anyway, it doesn't matter. So I'll pause here and I'll see you at example number 3 with a complex Thevenin circuit. Okay, so let's go for example number 3 now. Let's see. So now we can already see that the circuit is a lot different compared to the ones that we did before. And also we are going to try to find out this middle resistor here, A and B. This resistors name like R1, R2, R3, and R4. And this 12 ohms, 4 ohms, 6 ohms, and 8 ohms. And this one has got a voltage of 144. I thought about putting like 12 ohms, no, 12 volts, but I think that's a lot too short, isn't it? So I decided to go for 144 because like most of them are in parallel as well, and I want to have like high values. I guess, I don't know, I said I just put them randomly. I guess I could like make this on 120 and then 40 and 60 and then 80, but that would be too much to be honest. Anyway, so let's see. Oh, we did our first step, we choose the resistor we want to determine. Now let's go for the second step, which is finding it out. Well, because this one will become a source short. Focus, come on. There you go. This one will become a short circuit. So then there's nothing going through it, it's just an open circuit. Therefore, we are going to use only this section here. So we can redraw this as follow. We can do one resistor here, one resistor here, the two dots for A, B, R, T, H. Okay, one resistor here, and the fourth one being here. Okay, and then there's R1, R2, R3, and R4, and this one is 12, 4, 6, and 8. So about my drawings, like I don't know, I always do ugly and don't do like nice drawings, but it's understandable. Like there are the 4 resistors, and here are the, and remember RTH, you need to pretend that there is a resistance in here even though we don't know what it is and we can't see it. So oh, sorry, I want to like close the pen, but it's fine. So the step to find RTH is to simply find the total resistance. So we know these two are junctions, yes? So one way we can do it is to find out the parallel values between these two resistors and these two resistors and then add them together. Because when you eliminate the junctions, when you make the junction in one resistor and make this junction in one resistor, then it will become sort of a series resistor with those two. So we can write it as RTH is equal with R1 in parallel with R3 plus R2 in parallel with R4. Okay, so then this will be equal with 12 in parallel with 6 plus 24 in parallel with 8. That will be equal with 4 plus 6, and that's equal with 10. So RTH is equal with 10 ohms. I understand like this, it's a bit complex for how it's looking like, but you can't really do much about it because that's the way you calculate it. You calculate first the parallels and then you add them together because they become in series. Anyway, Actually, I think there's another way to draw this, which I'll show you right now. So I can also draw, instead of having this rhomb shape, we can make in like our usual rectangles. So let me redraw it here. So 1, 4, 4. Then one resistor here. There's a parallel one. There's another one here. There's one resistor here. There's that one for the RTH, and this is another one here. There you go. And then those 2 points here meet. This will be a plus, this will be a minus. This will be 12, 24, 6, and wait a second. Did I use 24? Oh yeah, I did use 24, didn't I? Yeah, I'm sorry. This one is meant to be 24, and this one is meant to be 24 as well then. I don't know how I missed that, to be honest. Yeah, sorry about that. And that is supposed to be 24 ohms. I should like pay more attention to the drawings, don't I? Anyway, let's see here. So that will be R1, this will be R3, this will be R2, and this will be R4. So you can already see what I mean by that. And you can already see that these two are in parallel with each other, because all of them are in parallel with those. Another way to do it, I think it's by adding R1 and R2, R3 and R4. Let me check if it actually works. So let's see. That'll be 12 plus 24, and that'll give me 36. So I'll quickly write here in corner 36. And then that will be in parallel with 6 and 8, which will be 14, wouldn't it? Okay, so now let's calculate this. So 1 over 14 plus 1 over 36. That'll give me that, and then that gives me, yeah, it's pretty much similar. It's 10.08. So I guess there are two ways to do it actually. I mean, okay, you can like also calculate these two, like you can also add these two together. No, sorry, add these two together as in series, and then calculate the parallel between them, and will give you a similar answer, which is 10.8. No, 10.08. It's up to you really, the way you want to calculate it. But anyway, now let's find the VTH, which will be here. VTH. And to do so, we can apply the Kirchhoff's voltage law, which will be flowing in this direction. Okay, so we'll make this one a plus and a minus, and this one a plus and a minus. Okay, so minus, plus, plus, minus. Okay, perfect. Well, it's also like this is plus minus because the current will flow through this direction and both currents will flow inside of it. However, VTH can only have either flow. It can either flow that way or it flows this way. So it adds up together. Now, I didn't really explain what Kelvin voltage law is. Well, basically what this law says is that inside the, let me draw a quick diagram. So what Kirchhoff's voltage law says is that, let me note it also, is that when you add all voltages, so let's say V1 plus V2 plus V3 plus V4, all of them will equal 0. And it doesn't matter, it can be used like voltages inside the resistors as well, and they will always equal 0 inside a loop, which means that at least one of these voltages will be negative, while the other ones will be positive, and will result in the loop having a being equal to 0 when adding our resistance voltages inside this rectangle. So you can easily, like, you can get creative and draw it as you see is simpler. You can either keep the romb shape and calculate using this shape, or you can calculate using this shape. You can use what I use, like calculating R1 in parallel with R3 and R2 in parallel with R4 and add them together to get the answer. Or you can just add R1 and R2 together and R3 and R4 together because they are theoretically in series to like get, and then calculate them as in parallel and then get the answer, the resistance. There are many ways to do this problem, really, like to handle it. It's more about like the way we want to do it. Anyway, now let's keep going. So we are going to need to find the voltage inside them. So let's name this one. Yeah, let's find the voltage in R1. So VR1 it's equal with R1 times V over, what is it, like R1 plus R3 because they're in parallel. Okay, and then this will be equal with 12 times 144 over 12 plus 6. That gives me 96 volts. Okay, this might be a bit complicated, but it's easier than like calculating. Like, you can either do this, you can either apply this formula and quickly find out the voltage inside R1, or you can go the long way, which is calculating the total resistance, then divided by the voltage, and then times it, and then separate the currents, and then finding the voltage inside the resistance. I would recommend you to this method because it's faster and easy, and the way it works is basically because there's a ground down here, that means there is no voltage difference between the ground and R1 really. So the way we do it is you do R1 times the voltage to find out the current, and then you divide it by the total resistance between those two, which will be R1 and R3, and then you'll get the voltage inside of it. Anyway, so yeah, but again, because it looks like there is something here, like again you can pretend it's a circuit, but because you are calculating the voltage, this is an open circuit, so basically the current flows in this direction and it doesn't flow through here. I cannot explain this simpler than that, to be honest, and I really hate that, to be honest. I don't like that one of the rules is that when you calculate RTH it's a short circuit, but when you calculate VTH it's an open circuit, because it makes it a lot more complicated, doesn't it? But we applied this formula before as well, and again this works because it's zero voltage in here and it's 144 volts coming through the top, and the difference of voltage is nothing really. So yeah, now let's calculate the next one, which will be this one here, R2, and we apply the same formula. So VR2 it's equal with, so we calculate first the current, which is 24 times 144 over, and then the total resistance, because they are resistance in series, we just add them together, and that one will be equal with 108 volts. Okay, now we have to apply Kirchhoff's voltage law. So as Kirchhoff's voltage law, we can see here what we need to do. So KVL it's equal with, let's start with this one, VTH. VTH is going from a negative to a positive, so it will be a positive number, so it will be VTH. Then we look at R1. R1 it's negative to is positive to negative to positive. That means it's a positive value as well, so it will be plus VR1. However, when you keep going with the flow with the loop, it goes plus to plus, so it's positive, positive, negative, because the two pluses matches each other. That will give me a negative value, so it will be minus VR2. Okay, so in case you didn't know, like I explained this before, but when two currents meet each other, then they will give you a negative value. Like when it's positive to positive, that's good. That means they have the same flow. But when it's a positive and a positive, that means they have different flows, different current flows, which means one of them has to be negative, like in this case here. So let's keep going. So then K, and all of it will be equal to 0. Okay, so we can move them apart. So let's move this to this side here. Yeah, that would be easy. So then VTH will be equal with 108 minus 96, and that one will be equal with 12 volts. Let me see if that's right actually. No, actually no. Sorry, that's not right. Okay, VTH plus 96 minus 108, and yeah, that'll give me 12, and VTH is equal with oh yeah, there you go, it's equal with minus 12. There you go. Yeah, I was afraid of that because in my answer book I got minus 12 and he gave me a positive 12. That means I did something wrong with just that one basically. So no, wait, it's still positive actually, never mind. I must like wrote it wrong in my how's it called, workbook then. Yeah, I did write it wrong in my workbook. Sorry about that then. Alright. So I wanted to show you something interesting, but never mind. So we're gonna to write here 12 VTH because this is a key component here. And then we got RTH, which is equal with 10 ohms. And then we got RL here. Okay, what I wanted to show you is that in when I calculated myself, I got a negative 12. I got a negative value, and I wanted to show you because like you can't do this and then write minus 12 volts in here. You know, you'll have to reverse the source. So if VTH was negative, then the schematic will be something like 10 RTH, and then that would be 12 VTH, and then this will be RL here. There you go. And that's what I want to show you is that okay, if the value is positive 12, then the voltage source maintains the same, is the same as in here, you know, positive negative. However, if this was minus 12, then it will be in reverse. It will be negative positive. So the current will flow downwards, back up, it won't flow up down. And that's important to know because I think it's a common mistake for people when they get negative voltage, they will disregard it. They'll be like, oh no, this is the wrong answer. While it can still be the correct answer, it just means that the component is reversed, you know. It's the opposite side. But anyway, so this is example number 3 with a bit more of a complex circuit, but we managed to do it. And I also showed you the KVL method as well to calculate the resistance inside the voltage inside one of the resistors, which is pretty interesting. And also I showed you the difference between them. Again, here we got 10 ohms and we calculate them as parallel because this is a short circuit. We see it as a short circuit. However, in here we see it as an open circuit because there's no current going through it. So we managed to use this formula here to calculate it, which is basically the resistance, the current going through R1 divided by the total series resistance between those two, between the ground and the top. Anyway, if you need like more help with this method here, I think I explained this in more details doing node analysis, because this formula is derivative from node analysis. Again, another one of the very useful ones, even more useful than this one, since you can use node analysis on literally any circuit. But anyway, so this was example number 3. I'll see you in a few seconds for example number 4. Okay, so here it is with example number 4. And this example is different because we got one voltage source and one current source inside the circuit. So I can show you even more how it works. Okay, so let's get started. First step, of course, it's noting the 2 points, because we want to find this resistance. This will be point A and this will be point B. Alright, now let's find RTH. So we can simplify this circuit, not really simplify it, like we transform this circuit into the following. So there's a DC, therefore this one becomes a short, there's a resistance of 8 ohms, and here it's nothing, this one it's an open, because as you know from superposition, it's a current source, so it's an open circuit in here. Then it's in parallel, and then the next one it's here, which will be the 10 ohms, and then this will be the 18, this will be the 2 dots. Okay, so there'll be AB, this will be 18, this will be 10, this will be 8. All right, so really simple. RTH is equal with 8 in parallel with 10, because again this one it's an open, yeah, there is a junction here, there's nothing in here, there's no current going through this direction, so 8 and 10 are in parallel because of the junction here. And then after we get them, there will become one resistance in here, so that will make it in series with this one. And because this is like kind of a short in here, it will go nicely, so that'll be plus 18, and that will give us 22.4 ohms. Really simple so far. Like when it comes to RTH, it doesn't really matter how many sources you have, since you may make all of them 0 and you literally just use the resistances to calculate. Anyway, now let's go to the next one, which will be to find VTH. And a way to find VTH is to apply Kirchhoff's current law. So we know this one, this here, it's in parallel with the resistance in here. So one way we can do it is by calculating the voltage VTH in this one here to get the voltage in here, because again this will be seen as an open circuit when you calculate VTH, so there won't be no current going through here. That means there is no current going through R3 either, which will make both of them equal. Okay, let's redraw it again, actually that will make it easier. So plus minus 100 volts, then one resistance through here, the current through here 6 amps, then another resistor through here, another resistor through here, the 2 nodes here, there you go, that will be 8, 10, 18, and this one will be VTH, and we are trying to find the VTH inside here. Okay, so again, when you calculate VTH, remember that this will be an open circuit, so the current will flow basically, we go in this direction, we go through this direction, you go through this direction, they will meet together, come this way, then some will go in here and none will go through here, because it's an open circuit. If the current goes through here, it doesn't have any direction to go, it can't go anywhere, it always needs to go back to the ground, where the ground is here. Okay, so now the way we can do it actually, it's by well, actually, if you think about it, this is not a good point here. It will make it easier if you calculate here, because it will be the same resistance, yeah, but I don't need to worry about adding up this one and this one, you know, and then to get this one out, because it's a junction and it's easier to do node analysis and Kirchhoff's current law in a node than is to do in a series. So let's see here. Let's name this one I1, name this one I2, and name this one I3. And I think you can already see where this is going. Basically, Kirchhoff's current law states that I1 plus I2 plus I3 will be always equal to 0. So therefore, VTH, now let's name it something else. Let's name it Kirchhoff current law is equal with I1 is coming in, so it's a positive. I1 is positive. I2 is coming in, so it's positive as well. I2 is positive. However, I3 is coming out, so I3 is the negative in here, and all of them will be equal to 0. Good. Simple so far. Now we can apply again node analysis in here, which will be the voltage 100 minus VTH over 8. Basically, it's the 100 minus VTH minus the voltage at this node divided by 8, because that will give us the current. This is basically I1. This one here, it's I1. Now let's do for I2, which is really simple, because I2 it's simply 6 amps. So it will be plus 6, and then minus I3. And again, I3 is VTH minus 0. So VTH minus 0 all divided by 10, because that's the resistance that the current goes through. Good. Now the common factor here is obviously 40, so we multiply this one by 5, we multiply this one by 4, and multiply this one by 40. So then we'll get, I wrote it down here, 500 minus 5 VTH over 40 plus 240 over 40 minus, I must put plus 26, 4 VTH over 40. Okay, so all of them have the same factor, therefore it's 500 minus 5 VTH plus 240 minus 4 VTH, which all of it will be equal to 0. So therefore minus 9 VTH, it's equal with minus 740. Therefore VTH, it's equal with 82.2. Okay, again, like it's minus 740 because you know you do 500 plus 240 and you move it to the other side, so that will give you a minus value. Okay, so then VTH it's equal with 82.2 volts. So let's remember this one. We already got RTH, so RTH is equal to 22.4 ohms. And again, this is actually really simple, isn't it? Because we got the current, it made the calculation to find the node voltage a lot easier. So now we can just redraw it. So it'd be, there you go, it will go in the up direction. That will be 82.2 volts plus minus. There you go, let's focus. And then it will go through here. There will be 22.4 ohms RTH. And then there will be the RL. There you go. We just transform this entire circuit here in a simple 2 resistors and 1 voltage source circuit. And again, like, I find this so valuable. I find them such a good method to like calculate, because imagine like having very big circuits made inside simple small circuits, and then you can easily control it. Like you can easily get whatever value you want inside RL and easily calculate it compared to the other methods. And also, this method is not long at all. It does take more drawing, to be honest. Like, yes, because you need to redraw the resistance and you need to redo the diagram again with the open circuit and then draw the currents. But it's a lot less calculating as well, isn't it? Because RTH, it's very easy to determine the resistance, especially when you have the diagram like that and you can see it clearly. And also, finding the voltage node is not hard enough. It's not hard either, because you're going to just need to find the parallel resistance to it, and then the parallel resistance will be equal with the VTH, which makes it simpler as well. Anyway, so yeah, this is another circuit done successfully. Okay, so remember, even though you have like 2 voltage sources, we can easily apply node analysis to it. And using node analysis will make it a lot easier, and Kirchhoff's current law as well, which both of them are very similar, to be honest. But yeah. Okay, I'll see you in the next last example, because there's a difference between using current and voltage. When you use current, it makes it a lot easier to calculate it, because current doesn't affect it that much. With current and resistance, you can easily find out the voltage. The problem comes when you have 2 voltages, because they'll conflict with each other, and you'll see so in the next example, which is example 5. And these 5 examples, it's like what I managed to like think about. Like, I don't know what other scenarios there can be, or like what other ways we can do it that it's different, because once you understand the basics of it, it's very easy to calculate it. Okay, so I'll pause here and I'll get a new piece of paper and we'll calculate next one as well. Okay, so here we are at the last example. In this one, I changed it a little bit. So I put, not only that I put 2 voltage sources, but I also put them to be opposite. This one going in the down direction and this one going in the up direction, to see how it affects the circuit. So we'll want to find RL. So let's put here 2 nodes, A and B, to mark the resistance I want to find. Okay, so and that was the first step. Now let's go to the next step, which is finding RTH. And for that, we're going to need to redo the circuit. So one resistance in here, and the other one is in parallel in here. These are shorts, because the voltage sources, they make short circuits, and that's why they are parallel. Okay, another one in parallel in here for R3, then R4 in here, then also the, let's say, invisible short, open, whatever you want to call it here. Okay, so that'll make it like a bit clearer for you. Now let's notate them. So that one will be 1.6k. Oh yeah, I also put like thousands now, because why not, just like a diversity to it, I guess. This one will be 8k, this one will be 12k, and this one will be 2.4k. A, B, R4, R3, R2, and R1. Alright, we got the R's. So now let's go for the next one. Let's calculate the RTH. So RTH, which is this one here, it's equal with R1 in parallel with R2, these two, and these two in parallel with R3, and then R3, all of it will be added together with 2.4. Why did I put 2.4? With R4. All right, now we can like rewrite it. So RTH is equal with 1.6 in parallel with 8 in parallel with 12 in parallel with 2.4. We can just put them without the case because all of them are k values, so it wouldn't make a difference, but it's important at the end of it to put the k value. All right, so let's keep going. RTH is equal with, let's see, 4.8 in parallel with 1.6k. I did this too, and then plus 2.4. This was supposed to be a plus actually. There you go. Alright, and then that will be equal with 2.4 plus 1.2, and yeah, it is 2.4 plus 1.2. It was this here. I was very confused about that. Give 3.6k. So RTH will be equal with 3.6k ohms. Alright. I mean, if you're not sure, if you don't believe me, this is the answer, then you can calculate it for yourself. You get the same answer, to be honest. Anyway, now let's keep going. Now that we know the RTH, what's left is to calculate the voltage. However, VTH. However, we need to do it twice because we got two voltage sources. So let's start with the first one. Let's redraw it again. So for the first one will be like this. This will be the open. This will be the other resistor, another resistor, and then here is the open circuit. There you go. And let's put the ground as well so that you can see it. This will be 2.4k AB VTH1, very important, 12k, 8k, 1.6k, and then this will be 12 volts minus positive. Alright, so this will be really simple because we only need to find this here. VTH1 will be equal to this value here, because again there's no current going through here. All the current will go through this point because this is an open circuit. So we can simply write as RT1, our resistance total 1, we need to calculate the total resistance. It's equal with 8k in parallel with 12, and then that will give me 4.8k, and we'll add it up with 1.6, because by calculating these two parallels we get the one resistance, and that one resistance will be connected to 1.6, and that will give me the resistance, which will be 6.4k. all right, now we can, I'll do both methods actually, I don't really mind. Okay, then we do 12 over 6.4k, and that one will be equal with 1.87, there you go, 5 times 10, oh no, sorry, that'll be equal with 7.5 times 10 to the minus 4. I think it is, let me check. So 12 divided by 6.4 times 10 to the 3. Oh, there you go, yeah, that's the first one actually. I already write it. 12 over 6.4k, it's equal with 1.875. Alright, and then times 10 to the minus 3. Alright, I guess I can split it up. So this will be for the 12, this will be for the 8k, and that will be 1.875 times 10 to the minus 3 multiplied by we want to find this, the current through this resistance, so it will be 8 over 20 k, and that will be equal to 7.5 times 10 to the minus 4. Okay, and now we can find out the resistor, the voltage through this resistor by simply doing 12k times 7.5 times 10 to the minus 4, and that will be equal with 12 times, I think it's 9, because like that's the voltage I'm supposed to get. Okay, and then times 7.5 times minus 4, yeah, there you go, it's 9 volts. So VTH1 is equal with 9 volts. This is one way to do it, but it's a simpler way to do it that doesn't require as many calculations, which again is through nodes. So we use this node here, and we can simply do VTH1 equal with, wait a second. All right, I'm back, sorry about that. Let's see, so then the other way to do it is with node analysis. And basically, we will do 4.8k times 12, and then we'll do 1.6k plus 4.8k. Basically, the resistance between those two times 12, that will give us the current, and then by dividing it by the sum of these two, it will give us the total resistance, and of course that will be equal to 9 volts. Okay, which again, like, these are two different methods to calculate them. Alright, now we found the voltage inside VTH1, like basically V1, we found the voltage through it. Now let's calculate when we try to find V2. We're going to notice like this is very similar to superposition, isn't it? That you need to pick up each voltage source apart to like calculate and find the value. So let's do it a bit smaller this time, so we can fit all of it in one page. So you got 20 volts, 8k ohms, 1.6k ohms, 12k ohms, there you go, 2.4k ohms, A, B, and E, V, T, H, 2. Usually put, I keep mistaking by putting E because you usually put E instead of V. They are basically the same thing, but I don't know, I feel like putting V makes it easier to understand, to be honest, since E seems like a strange value to put in. Anyway, okay, so again we can do both methods, but I'll just quickly use the one that I did. So it'll be RT2 equal with, again we are trying to find this this resistor here. It's not like we're trying to find a different one, so it's basically the same method, but instead of using 8k, we're going to use the 1.6k ohms, because these two are in parallel as well, 1.6k ohms G and 12 ohms. So 1.6k parallel with 12k, and that will give me 1.42, no, 412k plus 8k, and that will be equal with 20 over 9.412k, and that will be equal with 2.125 milliamps actually, because like to the power of minus 3. All right, we will apply the quick thing that we do this. There you go, that'll be 1.6k, that'll be 12k, 2.125 times 10 to the minus 3 is coming in, and then 2.5 times 10 to the minus 4 is coming out for the 12k for this one. All right, now we find VTH. So VTH is equal with 12k times 2.5 times 10 to the minus 4, and that one is k is 12k, by the way, it's 10 to the power of 3, in case you didn't know that. Anyway, it's equal with 3 VTH2. So VTH2 is equal with 3. Right now, VTH will be equal with VTH1 minus VTH2. And that would be equal with 9 minus 3, and that would be equal with 6 volts. And there you go. We got the answer that VTH is equal with 6 volts. Now, let me check. Oh, there you go, it's blank. Now, if you want to can like draw it again, we can draw the voltage source here, 6 volts plus minus, and then put here the RT, which is 3.6K, and then here the RL. There you go, RTH, VTH. Okay, and that's the answers basically. VTH is equal with how is it called, with 6 volts, and RTH is equal with 3.6K ohms. Now you may wonder like why here on the last step we took them away, we did 9 minus 3. Well, it's because they have different directions, as I showed you. This one it's a negative positive, and this side it's a positive negative. That means that they have different flow directions, and that means one of them has to be positive and the other one has to be negative, which means that we have to take them away. If both of them had the same direction, same current direction, then we'll add them together and we get another VTH. But because they have different directions, we just take them away. If you want, you can apply Kelvin's current law in here to like check out if this is the correct answer, and it is the correct answer. But anyway, yeah, that'll be 6 volts. And those are the 5 examples I did. I did more for this Thevenin theorem because, well, it's very important in the first place, and it will be very helpful in like further circuits. Well, at least I think it will be very helpful. As I said, I'm a first year in engineering, so like I just finished now, this is the summer holiday, and I want to do these videos as a recap of what I studied, which is kind of strange though, because this is the point where we stopped in electronics. We also did op amplifiers, which they are fine, I understand them, and we did very little on transistors and diodes. And these ones I need to recap myself to better understand and show you how to use and to do it with transistors and diodes. And another problem that I found is that we were supposed to do AC circuits as well, but the outbreak, the virus happened, so all the classes stopped, so we didn't do them anymore. And I'll have to like study AC circuits and show you how to do them. I'll have to also look up capacitors and inductors, and also show you how to do those how to do them as well, because I think we're supposed to study them in the first year as well, so it would be helpful if I know them for the next year. And I guess they make it an interesting video subject as well for like in the future. Another thing that I want to mention is that I'm not sure if I'll do Northen theorem or not, because I think I'll do only 1 or 2 examples of it, because it's not useful to be honest. Like Thevenin, it's amazing, you know, you can do it, you can find any resistor. With Northen, it's a bit more complicated because it doesn't really use its voltages, it uses currents more. And not only that, but it doesn't, at the end product, you won't get something like that. You're going to get a parallel resistor, like RN will be resistor Northen, and RL will be in parallel, they won't be in series, which will make it, I don't know, I find like it's going to lose its usefulness, because you know it's all about quick calculations when you change it in the series. If you make it into parallel, it'll make it a bit complicated to like get the right currents and everything. But I don't know, we'll see. And I don't think I'll go with Northern in such in depth like I did with this one as well. And I tried to like keep the videos under an hour. So, but I think this one went really quickly by because we quickly did the calculations. There wasn't that much explanation to do. Yeah, it's been like I had to explain more with the first one, so you know the basics. But after you understand the basics, and you can see the similarities between Thevenin and superposition, it's really easy to calculate and determine it then. Hopefully you are finding these videos useful though. I usually post them only once a week because like it takes 7 years until people start noticing them. So yeah, that's why I don't really post that often. Plus I like study myself as well. I need to like prepare before doing videos and stuff like that. Like coming up with different types of like circuits and stuff like that. That's why I do it only 1 day a week. But anyway, hopefully you enjoyed this video as well. And probably I'll try to do Norton today as well. If not, it'll be next week. And if I manage to do Norton this week, then next week will be delta star, delta y, and delta star transformations. So see you next time then.